Very good morning, everyone. Welcome to this edition of the Matrix Seminar Series. Before I introduce the speaker, Dr. Dilpan, I'd like to tell you a very small story in 1 minute. So in the ancient time in India, there used to be a guy called Eklavya, and he wanted to learn archery from the best archery teacher in India called Dronacharya. But he couldn't, the professor, the teacher, he couldn't allow him to teach under him. So what he did was he put a statue of him and started learning archery. So when I started my PhD, I wanted to work with him, but I couldn't for some reason. Then I kept working with him. I studied his literature, his studies, and I worked on silicon photonics. And then I'm here with him, inviting him to this talk. I'm very grateful. So here we are with us Dr. David Pan. He is a great researcher. He is a Silicon Laboratory Endowed Chair Professor in the Chandra Department of ECE at UT Austin. His research interests include EDA, electronic design automation, synergistic AI and IC4 optimizations, design for manufacturing, hardware security, CAD for silicon photonics and emerging technologies. He has published about 480 referred journal conference publications and 9 US patents. He has been he's the general chair of many prestigious conferences called DAC, ICCAD, ISPD. In fact, he got the DAC Top 10 Author Award and many other awards. So if I keep continuing, the list is endless. So please, Dr. Pan, the stage is yours.
Can you guys hear me okay? All right, it's a relatively cozy room, so yeah, feel free to ask me questions even in the middle of my talk, but I'll be more than happy to have Q&A after that. For the people on the Zoom, I guess we'll handle the questions towards the end, right? Okay, so yeah, it's really my great pleasure to visiting UTSA. Although we are so close, right? So we don't really get a chance to visit that much, but really, there's a lot of excitement here. The building is grand, and this is a new office and a lot of even new activities. The Matrix AI Institute is doing a lot of amazing stuff, and the semiconductor initiative, right? So what I'm going to talk about today is closing the virtual cycle of photonics for AI and AI for photonics. So it's not working. Oh, just give me a second. Yeah, all right. All right, now it works. So my talk is covered basically how light or photonics can do for AI and machine learning computing workload, and meanwhile, how we can use AI and machine learning to help build better photonics hardware, okay? So as we know, these slides haven't been quite updated up until 2022, but the growth trend is still, I mean, amazingly true in the sense that the ML computing load, if you think Moore's law is amazing, every 1.5 years or 20 months, your number of transistors double, right? But in terms of the ML computer kind of, like if you look at those, how many megaflops you can do, the compute growth is even way faster than the Moore's law. So every 3.5 months, it's doubling. This is truly amazing, right? And that's why nowadays the biggest semiconductor company is what? I'm sure you guys all know that the first $1 trillion company, in the semiconductor is NVIDIA, right? So it's, I don't know, I haven't checked it, but 1.1 trillion now, right? So probably, I don't know, if you look at the Intel, right, used to be the largest semiconductor company. It's probably less than 200 billion, right? So you're talking about 5 times bigger in terms of the market cap, right? Thanks to all this AI and ML workload demand, look at the largest models. You have many, billions or, maybe soon close to trillion of parameters, right? Training those ChatGPT and so on and so forth. There's a big arm race there. So of course, in that sense, you do need to have a lot of not only just the GPU kind of things. A lot of companies like Google and traditionally system companies like even software companies, right? Amazon that design their own chips, and of course Intel, AMD, and they have their own big chips. But even Amazon, right? So they have their custom AI accelerators and so on, chips, right? So that's why we do need a lot of specialized and domain-specific computing hardware, one is fast throughput and all these things. Another is energy efficiency. Actually, I don't know whether you have seen some data. They say the largest, like data center nowadays in terms of power consumption is like San Antonio city. It's like amazing. Because think about it, your stamp-sized, this chip, right? You are talking about the power consumption of 100 plus watts. First of all, how do you get the, heat out is another big story. But think about it. You have not only just one chip, you have millions of these chips, and then you build clusters and you build servers. That's why all these big compute servers, and you are talking about the city of San Antonio's power consumption. So this is unbelievably impressive. And but then energy efficiency is a huge deal, right? So I mean, conventional even right now, right? Okay, you can see the point. So if you look at the compute density, in terms of teraflops per millimeter square, and also energy efficiency, right? So the classical digital electronics is somewhere here, and then of course you can have neuromorphic electronics, which a lot of companies are working on that, right? AI accelerators. However, then there's also some optical and electrical hybrid kind of chips nowadays. There are also actually quite some startups. And even Google recently, in their newest TPU5, they have announced they're using photonics to do all this, high bandwidth connections, interconnects. But ultimately, if you want to push further, right? So there are actually, if you look at if you could have a fully optical, this is of course the dream, right? So then you can have really order of magnitude kind of energy efficiency and also compute density, right? But of course, we are still very, very far from there. So people are trying to first, we will do optical electrical hybrid compute, maybe 10 TOPS per watt, which is way better than this. But meanwhile, there's huge, like 10 to the order of fifth order, potential to combine neuromorphic photonics if you can do even full optical chips, right? So there are already many other things people are doing, right? So analog computing and all kinds of neuromorphic architectures. So of course this is a dream. So in terms of the electrical computing versus the photonic computing, right? So photonic definitely, we know that the speed of the light is the fastest, right? There's a physics limit there, right? But because of this, photonic device can do some really nice thing. So you can do computing, indeed. Of course, currently most computing is still done by transistors, right? So to do AND NOR gate and stuff like that. But you can also do digital computing using photonics. We actually published the Nature Communication paper a few years ago. You can use those microring and some structures to do digital nano. But that is not really the really big bang, because usually optical devices are very bulky, right? So although, in terms of, but they are very energy efficient and fast, right? So if you have some very specialized computing workload, stuff like that, yeah, using that is fine. But another really nice thing, which also recently there are tremendous efforts, like using optical device to do analog computing, essentially directly, using the physics to do the computing. So instead of compile into some digital thing and then do all this, right? But then you can offer tremendous amount of power and energy efficiency. So this is basically, when you have electronics, right? So you are talking about hundreds of nanoseconds if you want to do an adder or something like that, right? But if you're using or matrix multiplication, something, right? So here you are talking about the nanosecond, right? And then optics also provide some really massive parallelisms, right? If you use different wavelengths, so they don't interfere with each other. That's kind of nice. Electronics, if you have two wires cross each other, you say, hey, short circuit, right? But if you are like optics, no problem. They're all different wavelengths can coexist. So one physical kind of waveguide can actually transmit many signals, right? So that's also another thing that's very, very nice. And in terms of energy efficiency, again, right, for example, if you have some passive device, and as shown by, there's an IBM Nature Photonics paper 5 years back, right? So if you are just doing an inference engine, you already customized all the way, all this have already been tuned, your light comes in, And then this middle part, essentially kind of, you can think about is implementing some kind of matrix. And then light comes out is already matrix vector multiplication, right? So if you can do that, pretty much you don't consume any power because it's just light in, light out, and very little power. But of course, there's other things. Oh, how do you do optical and electronic conversion? And there's some analog to digital conversion. So that, of course, will become your bottleneck, right? But if you're just doing the other part, that's like really energy. So then the key thing is that how we can try to minimize the usage of this, conversion, right? And so on and so forth, right? So photonic AI has really been booming in the last 5+ years. This is just some selected papers in the last few years. Some of these are what we have been doing. So there are different architectures and different, different device people have been designed, and then doing circuit and a device circuit algorithms, architecture, whatever. Co-optimization is very, very important. And there are actually already quite a few, probably close to 10 or something like that, startups, right, doing this kind of optical AI. For example, the two most famous one, Light Matter and Light Intelligence, those are both spin-off from MIT. They're co-first author of MIT paper, and then they split and then become competitors now. No, I'm just kidding. So, which is good, then you can advance state of the art. I think they got hundreds of millions of VC and investment. So then, meanwhile, there's also different tools like from cadence synopsis, ANSYS to provide those kind of tool support. In terms of the PDK and the tap out, right? So optics there's no such thing called TSMC for optics yet, right? This is still relatively much, I would not much less mature. But the big companies are getting into it. For example, Global Foundry, right? And even I think TSMC, they are definitely working on some of that. So we just need to find killer applications. There go more in. So at this time, there's like the US has this AIM photonics, and then there's different foundries like AMF from Singapore and so on and so forth. Global Foundry definitely I think is probably leading in the hybrid, combined electronics and photonics in terms of foundries. Power is it's based in Singapore. Oh, sorry, so Israel. I think there are more advanced packaging, kind of, or some specialized. Right?
We have them in San Antonio.
Oh, really? I see. That's nice. Okay, yeah, maybe we can check them out. I don't know whether they are doing photonics, right? But yeah, it's a specialized kind of foundry, right? Is there? Okay. So. Yeah, let me just give you a little bit of basics for photonics AI, right? So that you kind of see how it works, right? So in photonics, right, the basic device, there are all kinds of devices like resonators and so on and so forth, right? So basically, if you want to do scalar multiplication, right, you can have to implement in photonics, right? Your light comes in, goes through some light modulation, this alpha, so you can then the y will be equals to a times x, right? Then if you want to do some matrix multiplication, again, you have x1, x2 here, then this one, once it is kind of configured, you can then, again, do some kind of matrix multiplication. And this is also, basically, you can kind of then build some kind of photonic tensor core, light in, light out, and then it's kind of analog. Essentially, it's an analog computing. You are using physics to do the computing. Then the device, there are like, of course, there's a linear part. There's also non-linear part. You have absorbers, and you can even have some optical RRAM. And then, of course, you need optical and electrical and optical conversion, right? Stuff like that. There are basic device like that. But in general, right, optical device, because of the physics, their dimension is much bigger. If you are for transistor, you are talking about, now nanometer, right? 3 nanometer, like 5 nanometer. But for photonics, easily you are talking about 1,000 times bigger because somehow because of the physics nature, right? So photonics, but they are very, very energy efficient. So that's why I think to totally replace the CMOS, it won't be practical. But if you have some really, very important, because nowadays silicon areas in general cheaper, you can have massive, so sometimes if you work on computer architect, people are even talking about dark silicon, so because you cannot, if you have so many billion transistors all turned on, man, your chip will fry, right, very soon. So so in that sense, you can have some area, pretty big area, dedicated for some optics. If they consume very little power, then, hey, go for it, right? If you can get thousands of times all this kind of PPA metrics, right? So, but as I already mentioned, right, so there are indeed still challenges, like one is the area cost, right? So for example, if you want to build some of this 8-bit adder, right? So if you're using photonics to build it, you're talking about maybe 140 times 200 micron square. But if you're using CMOS, 7 nanometer is only 5 micron, right? So the area is definitely much bigger, okay? And then there's also some robustness issues, right? In the sense that, CMOS has been developed by 50 plus years, people have really, spend, I don't know, probably trillions of dollars trying to optimize all this manufacturing process, right? And photonics may be also sensitive to temperature and some kind of variation. I mean, electronics also have some of this, right? But people know how to deal with it nowadays, right? They live with it. But photonics, there are some variation issues. And then also there's something I would like to call it versatility, in the sense that there's a general purpose CPU and all these things, right? But general purpose optical is still an issue, and even for AI computing, as I'll show you soon, right? Because the AI model changes so quickly nowadays, right? Like when we do deep learning, there's CNN, DNN, right? But now the hottest is transformers, right? ChatGPT and those stuff, right? So for language model, so then the underlying thing is different. So I'll show you some the recent work that we just got accepted at HPCA. So to try to address the transformers, right? Early days, all those are for inference engine, maybe matrix multiplication, right? So anyway, we are trying to handle some of that issues. And then adaptability, in the sense that most of the previous like optical chips or that people have developed just mostly trying to do inference, okay, meaning with a fixed weight, okay. But if you do training, you have to change the weight. Anytime you change the weight, it will take time. You have to tune those optical devices. That will cost energy, right? What I have told you is a good part, but there's other part that we haven't talked about. Right? You have to tune that, like the phase or thermal, or something like that, right? So then how we can make it more adaptive and still save overall energy efficiency and so on and so forth. Right? And also, of course, a lot of optical device, by the way, at this time, mostly when people try to design it is manual design, right? So they run a lot of simulators and try to figure out, hey, if can we have like efficient design, like in electronics, right? There are all kinds of commercial, really nice EDA tools. Right? For photonics, there are very little. So how we can have a design efficiency for those, right? So that's why what I mean is that previous several ones maybe how we can use better photonics to develop a future AI accelerator. But meanwhile, also, can we use AI to help design those, optical chips? Right? So with all this, we need like hardware, software, and co-design, and also efficient design automation. So that's why I call it a virtuous cycle, photonics for AI. And then once you have better AI, faster AI, more energy efficient AI, you can use that to help you design better, photonics itself, right? Okay, so over the last, I think we have been working in this area for, I have been collaborating with Professor Ray Chen, my colleague at UT Austin, a lot. So his main area is more like optical device, optical interconnect, and I'm more like in the system level, CAD and so on and so forth, right? So we have really a great partnership, and we have a NURI project, which we're finished like soon, but we have some newer project and so on and so forth, right? So we have been touching different aspects from the computing hardware aspect to circuit model co-optimization and also deployment and applications for various. So here I just showed you some examples of the work, right? We have published many papers. So this is really interesting thing of this is a very, very interdisciplinary, right? So because it's just so new, right? So it's not like a CMOS, it's very clear roadmap. Here, there are like so many, like a domain you can work on. So we actually touched a certain new novel device, and this kind of device, how I'll show you some of this device aspect, and then how do you build better models, and also how do you like deploy it and to do training and so on and so forth, right? So ultimately, essentially, how you is try to address the previous like four or five limitations that I talked about, right? So how can you have more efficient, and how do you make it more adaptive, and how to make it more reliable, and so on and so forth, right? So due to the time limit, I will focus on a few work to give you a sense so how these different things work together. So the right-hand side essentially tells you about area efficiency and how do you address versatility, how do you do like design efficiency. In that sense, we were develop a better photonics device, right, using AI, and also how do you make it more robust. So all right, so let me actually talk about the first work, which is a butterfly style optical neural network. So in that sense, it's more for area efficiency, right? So why area efficiency is a big deal? As I already showed you, each optical device, for example, like MZI or those, they are, in terms of the dimension, you are talking about thousands of times, 1,000 or more, right? Compared with the transistor, right? So, but that means we have, much less, in terms of number of devices we can have on a chip, right? So then how do you? The question is that, hey, can we use less or more, right? So instead of using so many transistors, we can use much less number of optical devices. We can still do the same thing. That will be nice, right? So this is the paper from the original MIT paper published in that actually helped to spin off $200 million spin off like companies, right? So what they have, they show that, hey, you can basically to implement the matrix and vector multiplication, right? So that the bigger matrix, you can do some single value decomposition and so on and so forth, and then you implement using some thing called MZI array. This is kind of don't worry about the details, but essentially some optical device, you kind of configure them, and then you set the phase and those configure them properly, and then you can do it, right? But the thing is that the area is big in the sense that you need ON square of MZIs. So what we found is that, hey, instead of using this kind of general matrix, we found that actually even in the machine learning community, right, people found that, okay, when we train your neural network, right, you not necessarily need all kinds of weights, right? You kind of have, you probably heard about compression, pruning, and those kind of terminology, right? So many of these may be zeros, right? So you can use much less number of weights and can still get reasonably good accuracy. People even use like instead of 32-bit weight, they can reduce it to 4-bit and still, wow, works perfectly fine, right? And then there's also for example, in these machine learning models, right? Instead of using, you kind of use a very general matrix. We found that this is a contribution from the main machine learning community. They found, maybe I can just use some matrix called a circular matrix. Essentially, excuse me. Essentially, it's not a very general matrix, but you kind of circulate the values, right? So they can still work very well for those kind of, if you want to train a machine learning model to detect the cat or dog, it's fine, right? So then we found that if you are configure, you kind of constrain yourself to that kind of matrix, we actually can use something a very compact butterfly structure. So that means the number of devices instead of is n square is n log n. Okay, so then actually we can deploy it. By the way, this is a paper we originally published in ASP.DAC 2020, 3.5 years ago, almost 4 years ago. We got the best paper award. But after that, we said, hey, this is so cool. We should try to tap out the chip. Indeed, actually, we tap out the chip, through AMF, but it got us a lot of time students, how to test it, because optics is kind of relatively new, right? So we come up with this idea of got that paper, and then we actually even spend money or these things to get the chip tap out, and then we package it. But then we found that to do the measurement is actually quite some challenge. How do you measure it and really deploy it and show that it can work for this even mini those kind of this kind of test, right? But anyway, we have done all this. We design it and we tap it out and we evaluate on real machine learning tasks, right? But the cycle is quite long, right? So as you can see, and then we published the paper at ACS Photonics, is one of those. So in last year, so this is a chip that we tap out, and so let me see. So we then using this to evaluate on several machine learning tasks. So this is a small task, like this is a MNIST, right? It's a very simple kind of only 2 layers of CNN, right? No problem. We have got 94% accuracy. And then there's some CFAR, right? So you can detect the holes, so and so on and so forth. Right? We actually, during the COVID, because this project happened during the COVID, right? So we also got some COVID benchmark, like a chest X-ray. So and we also found very good accuracy. And excuse me. So we even compare with some like a Nature paper, which using RRAM, right? So even that, right? So their accuracy is actually not as good as, I mean, similar, right? I would say, right? So that means, this kind of, we are essentially, as you can see, our key idea is try to customize it. And once you customize it, in terms of potential peak compute density, we're talking about hundreds of tera ops per millimeter square. So if you compare with this A100, it's, as you can see, if you look at the numbers, right? So we are way more than that, right? This is, of course, we are assuming perfect assumptions, right? These are like a peak compute density, right? So, and also compare with the original MIT paper. So, which, because instead of, remember, when they grow, they need O(n) squared of number of devices. We only need n log n, right? And so we can reduce like area by 2 to 4x. But in terms of also delay, because we have the throughput, the delay is actually much better. It's like a factor of 10 times, right? So these kind of things actually, as you can see, is a specialized photonic ML engine. And so actually, after we publish this, there are a lot of follow-up works related on this, because the original paper from MIT, they are trying to have a universal linear, like a matrix multiplication, right? But our butterfly structure, essentially, as you can see, is a specialized hardware for subspace linear, which actually also works very, very well for many machine learning tasks, right? So there are a lot of also papers published along this line, right? So how to generate those specialized hardware for subspace optimization, right? So again, right, customization and specialization, right? So depending on the workload, you can actually get orders of magnitude, efficiency, right? All right, so far I have talked about basically this, still using more conventional, like a MZI device. It's a very robust and widely used device, right? But now we are also, by the way, when people are first using MZI, those devices could be 200 micron or something, right? But then you can also, on one hand, if you talk to optical device people, they always try to, like, in CMOS transistor, you have like 1 micron, 6 micron, and now it's 14 nanometer, 7 nanometer. People are also working to improve make the device smaller, right? So this is kind of scaling is also happening there. But but on the other hand, can we break through the compute density bound in the sense that one device you can only do one operation, right? So we actually tried. This is something very interesting idea we have done. This is also use other paradigm to do area efficiency in the sense that we call it a squeeze light. We published and also we tap out the chips and so the key idea is this, right? Usually, let's say if you have one device, you can only do one thing, right? But those devices are pretty bulky, right? So what's the key idea here, right? This is a multi-operand ring, micro ring. So in the sense that typically in the past, one ring only have one control. You can do some stuff. But now we say, hey, can we kind of segment that one device, you know, into which is controlled by 1, 2, 3, 4, whatever can number of controllers, because these devices are pretty big anyway. So maybe we can chop them into sub-segments. Each of them can be controlled by each different xi, right? And then what's the beauty of this? One device can do, you know, matrix multiplication and summation, right? So this kind of stuff like that, right? And then there's also, we are also tap out some multi-operand MZI, and we are also doing some multi-operand MMI. Don't worry about the details, but essentially the key idea here is like, you can think about one transistor, you already just do one thing. But now, because optical device is pretty big anyway, so we chop into sub-things, and then you can have one device do a bunch of things, you know. Basically, your light comes in, goes through this circle, and then it will perform this kind of computation. Okay. Wow, if you can do that, that's why we call it a squeeze light, right? Oh, yeah, question?
On this ring kind of architecture, how do you realize that in hardware?
Oh, you know, you fabricate this kind of rings, right?
Would it be, is it area efficient?
Huh?
Is this structure area efficient?
Well, you know, what do you mean? This is basically a fundamental device in the optical, right? Is a ring structure, right? But basically, yeah, this is a very widely used a fundamental structure. It's like a transistor in, you know, for CMOS, right? So a ring. Well, of course, there's a waveguide, there's a coupler, and there are some, you know, but the ring is one of the very widely used structure, right? So basically, what we are trying to say here is that, hey, you know, essentially, instead of entire ring controlled by one X, now I have you know, I kind of chop into several components, and then we actually tap out a device using UT's fan, but we couldn't afford the most advanced one, so we used the thermally control. But indeed, you can kind of, we verified it. Oh, your light comes in, you can actually do this kind of operation like this. That's pretty cool, right? So, and so. Then with this, you actually also have some built-in nonlinearity. Again, don't worry about the details here. So you can also basically use this to do different controls. And the key idea now is like, all right, so now if you want to build some optical neural network, essentially in the past, you need many, many rings to do this, right? But now one ring can do that, right? So that's nice. So we can actually using, don't worry about the details, but basically, you know, essentially the basic components is this multi-operand ring, and then we can build like a differential structure in the sense that you can handle both positive. You know, you do have negative. Sometimes you have negative values, right? You need to be able to do that. So no problem. We'll have a differential rails to support positive and negative neurons, and then the learnable part are those different factors and so on and so forth, right? So again, don't worry about the details. So essentially, once we do this, oh yeah, question? Yeah.
Is every operand in that ring connected to an optical node?
Huh?
So is operand either connected to node or frequency, the small operand in this ring?
Yeah, each of these is a ring, right? Then you will build an array structures, right? So then, you know, you will go from here, then you can actually do bigger operations, right? Stuff like that, right? Yes. So I think once we do this, compared with the previous ONN, right? So because now we squeezed, you know, basically instead of using so many rings to do it, right? One ring can do a lot of things. So that's why we can reduce the number of device usage significantly. And also, you know, or you can use less number of wavelengths, right? And so on and so forth, right? So this is actually the key idea, right? So again, right, I think I won't go into details, but it gives you a sense how, you know, we can kind of do device level, you know, innovations, and which were, you know, worked well with the architecture. And then we need to develop, of course, I didn't go into the details, how to do algorithm development together with these kind of structures. Yes.
So between the ring and the Alexander and the MMI, I know the MMIs are bulky, right?
Right.
So what is the most accepted or most practical implementation amongst the three?
Yeah, this is really a great question, right? So MZI is a very robust, more like bulky and more like because again, right, this device area is still like how should I say? Because they are not like a CMOS, they are huge, industry investment. This investment on this kind of optical area is still much less, compared with. So we need the first level tier 1 fabs to spend a lot more money, and then you can kind of But in general, my ring is much smaller compared with the MZI. But then we also show that you can directly use some basic components, instead of putting them together as a micro MZI device, but you can actually, like our butterfly structure, we directly use those, kind of primitive device to build the network. So the ring also is smaller, and then there's also micro disk. Right? Yeah, so so all these are still a lot of development. Right? Yeah, yes. So now, once we have some of these, right? Next, I'll talk about this the new paper that just got accepted probably last week, HPCA. So we actually developed the DOTA. It's the first photonic transformer accelerator. Well, why transformer, right? So as we all know, right? So for the deep learning kind of innovations, right? So CNN, DN, that's the first thing to come out. Then people always come up with, if you go to NeurIPS, wow, there's like 10,000 plus people, right? And so by the way, we also have some papers there, right? So, but the things that the people always come up with new, architectures. They found, oh, wow, because of the large language model and so on and so forth, and people have transformers. But then the workload is kind of different, right? The reason here for workload, for example, transformer, right? You will have a dynamic matrix multiplication. So when we previously, when I say it's not dynamic, right? If it is inference, for example, your matrix and multiplication, stuff like that, one of the weight matrices is fixed, right? But if you are doing, transformer and those, the full range, right? You have X and Y, they're all changing, right? So this workload is quite different, and you have full range of values, and also you may have real-time and frequent operand switches, right? Not like this, your W is fixed, right? So then the existing photonic tensor cores for transformer is not good enough, is in the sense that if you want to handle non-negatives, and because previously maybe you handle non-negative, if you want to handle negatives, you have to kind of do some differential structures and stuff like that. Then it will be 4 times more. So you essentially you need to deal with that. And if you want to handle like a mapping, right? If you are using MZI arrays, right? And you have to do all this singular value decomposition, and who will do that, right? So then you need some other facilities to help you to do that, and so on and so forth. And then if you want to program, during the training, if you are changing the weight, you have to have some program to control. Hey, adjust this phase and stuff like that on this device. Then who will do that, and that kind of configuration programming also takes time. There may be loss and so on and so forth, right? So what this is the first one is inefficient for the full range, right? Because if you want to have negative values and all these different ranges, right? So, and then also you may have to change your weight and so on and so forth, full range X and Y, right? So it's not as versatile. So what we proposed at the upcoming HPCA is what we call dynamically operated photonic tensor core, DPTC, dynamically photonic tensor core, right? So it's actually a crossbar style photonic tensor core. So we can do one-shot general like matrix multiplication. So again, I'm going to show the details, but basically the idea is like we actually can do direct light and light multiplication with some high-speed encoded signals. So you have light here. You can basically do the direct multiplication, and then the signs are encoded by some coherent interference designs. And then we also have WDM, wavelength division multiplexing, which actually can have multiple wavelengths, so that we can do spectral parallelisms. And then one nice thing, by the way, in the past, right? So why people have to use so many electrical optical conversion? The reason is because, hey, I can do something, in optical domain very nicely, very fast, zero power, no problem. Life is good. However, if you have a lot of other things you have to do it in the electronic domain, boom, you have to do conversion. That's where a lot of things get not so good. But if you can kind of directly do this in optical domain, and then you have optical interconnect, everything optical, then you save a lot of conversion process. Yeah. Yes.
Sorry.
Yeah. No problem.
I think there are two things, right? Here you're showing the dot products and the multiplication that can be done very efficiently.
Mhm.
How about the nonlinear
Okay.
applications?
Yeah.
Because that's been a challenge. and
Yes. There are some optical device can do nonlinear.
Some of them.
Yes.
can do it now.
Yeah. Yes. I didn't show in details, but yes, there's an optical device that
And,
can do nonlinear.
You assume that you're not going to store any of these intermediate.
That's a great question. If you have something optical memory, wow, pure lovely, so this is still something. Yeah, I'm actually working with some. We have some discussion with some. Yeah, if optical memory, people have been tried in the past, but yeah, that's why. Well, if you don't have it, so you can also think about architecture change. Because in the past you store it, but hey, computer is so fast, you don't need to store, just compute. You're using more computer to replace the memory, right? So yeah, that's a great question, right? So how do we do the memory, right? So yeah, there's no optical memory right now, but you can use some phase change memory or some other things, and you can work together with it. But if you have some very native using photon to store the data, wow, that would be fundamental breakthrough. Yeah. Okay. So for our DOTA accelerator, basically it's a first customized photonic tensor. For transformer, right? That's why it's also using optically interconnected multi-core. And so in that sense, we can really reduce EO and OE conversion significantly, because we are only do it in the optical domain, everything as much as possible, right? So only so you offload the partial summation to some for the bit. All right. Yeah. So anyway, so I won't go into details, but we have shown that compared with the micro ring or MZI with the same area budget, we can have 3 to 6 times better energy efficiency. And in terms of latency, it's 7 to 100 times better. And this actually can handle attention network. And, so this is very nice. Yeah, so again, I won't go into details. I'll be more than happy to share you the preprint of our HPCA paper. By the way, how much is it until 12, right? We have time, right? Okay, yeah. Yeah. So, all right. So far I have talked about AI photonics for AI, right? Using different kind of photonics device and architecture and anywhere in the middle and combining them, and including algorithms to develop a better future photonic accelerators. There's definitely this area is very again, right? So there's no majority, because it's still a lot of research and a lot of unexplored area, right? So then once we have this kind of accelerator, right, how do we deploy it into a real, either training or inference, right? So if we want to deploy it in the real world, right, whether it's autonomous driving or edge or whatever, right? So how we can make sure those analog chips still work, if you have some reliability concern. As I mentioned, right, so one thing, for this photonic related accelerator, so they may be susceptible to temperature variations, so for our electronics chips, when people design chips, they usually will have worst case, best case, they have to handle all these process variations, right? For photonic, there's also these kind of variations. One is, you design it very conservatively, but another thing is that what you can do, for example, when you are deploying a machine learning model, you can actually have, because at that time, your chip, you can kind of do real measurement and then provide some feedback. So then one idea is that, okay, you will build a machine learning kind of model, deploy it based on whatever previous characterization, right? But then when you run it in real chip, because there's some change in properties. So then, originally maybe you are 95 accurate, but now boom, you deploy, you dropped it to like 90%. But what we are trying to do here is like my student, we also have some self-learnable photonic AI engine that basically can train itself, can do on-chip adaptivity, right? So this is like really, at that time, if you have some temperature variation and whatever, so they can, our engine can directly tackle the super. It's not even measurement. It's like inherently you got some feedback, then you can just use that real kind of on-chip data to help you to do the training algorithm, right? So that's why we call it like a scalable on-chip training. This was like 2 years ago. We have a NeurIPS highlight paper, but we also published a bunch of other papers related with this, right, including at DAC, right? So as I already mentioned, right, so essentially we want to make sure you have, while you are doing the training, it considers the robustness effect and online adaptability. Excuse me. So what's so basically, as I already mentioned, right? So hopefully you want to have accuracy drop when you are deployed, and also, in terms of latency stuff like. So if you kind of because in the past, right, people when they are doing this, they do like they do offline machine learning algorithm. They have the optical chip already, right? Then let me write down some online like training algorithms based on that property characterized. But then when you deploy it in the real chip, because the temperature and all this change, so the original algorithm may not work that well, right? But now basically we are going to do this, adaptive on chip, right? It's doing some what we call in situ training, right? On chip training. So that's why it's very accurate. We want to have drop because you are doing real hardware based training. So we have published several works on this. Including the, I don't have time to show the details, including some, at the beginning, we use some zeroth order feedback, then there's a first order. Which we can, let me see if I have, let me just show you some summary, right? So we have actually several generations of work along this line, right? So these are some previous work people published. So this FLOPS is the work that we published at the DAC 2020. And it was actually nominated for Best Paper Award at DAC. And then later on, this is the first work that is using zeroth order gradient descent. And then later on, we found that, okay, one thing while you are doing this kind of training, right? When you are doing training, one thing you are changing. What are you changing? You are changing the weight, right? But the problem is that anytime you change the weight, you have to configure that device. That's not good. If you but the key idea for this second work, we call it mixed train, is that we found that, hey, you probably can fix 90% of the weight. No, please don't change those guys. But of course, they need to be proper weighted, right? But then only change the rest 10% of the weights. You can still get really good accuracy. So in that sense, you can imagine, that's why we call it sparse coordinate design. So you can reduce the sparse, you can increase the scalability and the power efficiency significantly, right? And then this light, so is a work that we published at NeurIPS, right? So it's using a first order training, to get the feedback, right? So you can actually get, you can train a lot more, because remember, we are doing on-chip training, you only have so many devices, and then you won't be able to train so many parameters, right? But with this, we can actually on-chip train a lot of, the trainability can be increased by up to like 10,000 times, right? Anyway, I won't go into details here, but, this is for on-chip training, not just the inference, right? All right. Now, so far, most of my talk so far has been focused on photonics for AI, right? Remember, I want to close the virtual cycle, how we can use AI to help design better photonics, right? So how do you do that, right? Of course, there are many things that we have been doing. For example, how to use this to develop a better architecture, and you can using AI to help designing better neural optical architecture. But this is a work, Neural Light is a paper that we published at last year's NeurIPS. It's a spotlight paper. So the idea here the idea here is actually, I didn't, at that time, we didn't have this terminology, but it turns out to be, you probably heard about AI for science. It's a very hot topic now. So essentially, AI, what is AI for science, right? So using AI to help you, for example, solve some really hard scientific problems. So what are some fundamental scientific problems? For example, Maxwell equation or some kind of Navier-Stokes equation. To solve it of course, you have all kinds of like a finite difference, finite computational models, right? But if you want to do it very, very efficiently, they're just very slow because it's a physics-based method. You have to use a finite element and all this kind of grading, the stability, all kinds of things. However, if you can use AI to help you speed up that process, that's our idea here. So we can kind of leverage the physics and to build so essentially, we can have AI-assisted optical simulation, right? Because one of the very basic, underneath, when you need to use this, right, you have to use a numerical or some kind of very detailed simulators, right? So our idea is like, but running those simulators, they can be very, very slow, okay? Especially if you are trying to use it for, doing optimization, you are trying to explore your design space, running those kind of very detailed, physics-based simulation, is unaffordable, right? So what we have been doing here is like, hey, can we learn the light propagation principles and with some kind of, physics principle we guide it, but not using like very, very expensive simulators, right? So for example, to solve Maxwell equations, and those are essentially PDEs, right? This is actually a very, very big topic. Even I think NVIDIA, Anima, right, she's a professor at Caltech, but meanwhile also at NVIDIA is leading a group doing AI for science, climate change, all these things, right? So this actually is our work in Neuralight is in that principle, right? Essentially, it's inspired by some Fourier neural operators to solve PDEs, partial differential equations, very, very fundamental problem for all this scientific community, right? So we developed some physics agnostic framework for photonic device simulations. Again, I won't go into details, but usually, right, so to solve this is, you have to do the grading and you have to make sure it's stable and all these things. It's slow, right? So what our idea is, like, we're trying to do some inference and to do some parametric PDEs. And so essentially our neural is faster, right? So it turns out that when I won't go into details, but we have some new way to encode the PDEs and then develop some new neural operator models and then plus some training recipes. So by doing that, we show that, again, there's a lot of details, but basically we can get 200 times speed up compared with the, FD, I think finite difference, those kind of, detailed simulators. And but we have some of this is physics guided. You don't do everything, it's not like directly doing kind of just learning from data. You have some physics to guide you to while you are building those models. And but meanwhile, so it's still relative. It's not 100%. It's not as accurate as, of course, those detailed physics simulators. But overall speaking, they are very close. And if you are using it not as a final verification, but as an optimization inside some optimization engine, that's perfectly fine, right? So that's our goal here. So we found that compared with, by the way, people previously also have tried some of these, but compared with those previous models, we can get much lower accuracy and and much less parameters, and so on and so forth, right? So we can do it in real time. I know probably you cannot watch, but anyway, so it's really fast, and we can do real time optical field prediction. Anytime you change some parameters, and you can see the waveform. You actually. Sorry, probably you cannot see it very well, right? But anyway, so you can do real-time optical field prediction. And the idea of this, by the way, is that, think about it, right? If you have this kind of thing, then we are actually using this principle to help us to design better optical device. Like we have, I think, on some ongoing, actually even tape out using this to develop some multi-operant MMI, something like that. So because previous design space is very big, using those detailed simulators is just impossible. But now if we are 200 times faster, then you can actually use it to help design better chips. This is also another, because besides, today I'm mostly focusing on photonics and AI, right? But my group also works a lot on the AI EDA aspect. So in the photonics, there's a very interesting effort. I don't know, it's called inverse design. I don't know whether you heard about it. It's a very hot topic. Even there are startups trying to do that. But in terms of inverse design, so because different device structure, they will have different behavior. This actually principle can be used not only for photonics, but also, for example, last in August, I was invited. There's a ERS summit. I don't know whether you heard about it. I was there, and there was a workshop. I was invited to give a talk there. It's called Future AI for Millimeter Wave RF. Because a lot of these RF structures, like an antenna, you can kind of cast it into some kind of inverse design problem, it turns out. And then even people in optical lithography, I don't know whether you guys know this, right? So, when you're a transistor or like this is the mainstream transistor, I do a lot of this design for manufacturing work, right? Think about it, right? When you tap out your chip, you do VRSI design, you have a bunch of rectangulars. That's okay, you send it to the fab. But when the fabs got those rectangulars, they will say, oh, okay, sure, you followed my design rule. Okay, now, your job is done. But the fabs really have to make a huge massage of this mask you got from the designers. For example, they say, oh, okay, this rectangle and this rectangle, sorry, cannot be printed. Or make this part a little bit fat, so they play all kinds of tricks. So-called mask synthesis, OPC, optical proximity correction. But the most advanced ones nowadays is so-called inverse lithography, ILT. And even they do source and mask co-optimization in the sense that basically to print those stuff, man, you have to throw hundreds of like to do all this kind of optimization, right? So imagine if you are using very detailed simulations, it's just like so expensive, right? Anyway, so this is just related, not really directly photonic, but all related field. Right? Anyway, so let me try to conclude, right? So hopefully in this talk, I give you a sense like how we can, from device, like a multi-operant device, and then simulate, and then we fabricate to test it, to then propose new like structure, like butterfly structures, or like a new architecture to handle as I showed, right? This is our daughter work, HPCA, and stuff like that, right? So there are, we actually tap out chips, and we also released some software, right? My student Jiaqi Wu, right? He and other students have contributed to the open source PyTorch ONN, and so I think there are really a lot of potentials here. This is still, like a very new area compared with CMOS. Right? So people are also always asking, hey, what are the futures? Because we know that CMOS scaling is close to the end. I mean, of course, we are talking about 3D. But 3D and this are in the future. I think, of course, you probably have CMOS still the main substrate, but meanwhile there are like new memory, optical, and this and that, right? So to work together, right? So okay, so I hope that is gives a sense how we can use photonics for AI and also AI to help you build better photonic device and chips. Right? So yeah, last but not least, I'd like to thank my collaborator, Professor Rachel, and also our students. So some of them already graduated. Like a lot of this work is done by Jiaqi Gu. Right? He's now assistant professor at ASU, and also some other students. They're actually doing amazingly well, and our funding from Muri and so on. So thanks very much, and I'll be glad to take some more questions and answers. Okay, there are some questions in the chat, I guess. Okay. Yes.
You did a wonderful talk.
Thank you.
In your work, do you on-chip laser or off-chip laser?
On-chip laser. Okay, this is a really great question, right? So and most times so far, lasers are still off chip, right? But yeah, you brought up a really great question. I have actually, I didn't put it here. I have now an ongoing project. We just got funded, right? I work with an assistant professor in KAUST. KAUST, Saudi Arabia. Actually, I was invited. Even now, semiconductors everywhere. Even Saudi Arabia, they have money, oil money, right? So we have oil money too in Texas, but they have probably more. Okay, so King KAUST is King Abdullah, University of Science and Technology. It's a very nice campus. First time I visited there, right? They also have this semiconductor initiative. I was invited to give a distinguished seminar there, and then I had some discussion. They have a faculty called assistant professor Yating Wang. Yeah. So anyway, so she is an optical device person. She was a postdoc with John Bowers at the UC Santa Barbara, right? He's a very famous professor. So actually, her expertise is more laser, on-chip laser. So now, say, hey, we should try to do something. So there's some internal kind of cost proposal, something core and something. We have a joint project that actually funded now. So we are trying to build, to put that together, right? So they can fabricate a device and then also laser. I think that would be really cool, right? So yeah.
Mr. Chen, you had a question earlier?
Yes, so this is very good and very interesting topic. I'm not quite familiar with this field. So I have some research on the wireless.
Oh, wireless.
Yeah, so I think there's something we actually can migrate, like the analog from wireless using for AI. Yeah, so
analog
through the modulation.
So are you in the wireless kind of communication network? Or?
Yeah, somehow it's like I'm on IoT, so it's like very.
Yeah, so of course, I think in terms of wireless, you can have optical interconnect. You could also have wireless interconnect.
Yeah, like
RF, right, right. Yes. That's true, right. And if you're talking about hardcore analog, right, actually, I work a lot on machine learning for EDA. So we do machine learning for analog chip designs and RF for some part of the transceiver designs, right? So yes.
Yeah, maybe we can talk.
Sure.
Later.
Absolutely. Yeah.
Thank you.
Yes.
So I have a question. So you had this slide on the on-chip training, and you said that you train only 10% of the weights, whereas 90% are not updated.
Right.
I was thinking, what was the criteria for deciding which 10% was it?
Okay, that's a great question. Sure. Of course, you have to find those. Yeah, this is kind of during the training process, and somehow we find you just kind of decide, okay, these guys, you figure out those guys, changing them probably won't matter that much. You will fix them, right? So yeah, you only change because anytime you change, you have to tune it and stuff like that. So we basically only change. There's some algorithm to decide that. Right? I can refer you to the paper.
I have another question, which is related to the first part of your talk. I'm not very familiar with photonics. I was thinking, when you do the ML inference, how are the inputs represented in light? Because you can represent them in frequency or amplitude or phase.
Okay, yeah. In our case, the light intensity, right?
Light intensity.
So basically you have several light comes in and the light intensity. And then somehow you go through this optical device. You can think about this is a vector. And of course, if you can do vector matrix, you can do matrix. Right? But anyway, this is a vector and this is a matrix. Then output is a vector. This middle part is implemented by optical device. So it's light intensity. So you then at the output side, you will detect light intensity.
Does phase synchronization, play a role in it? Because it is intensity then.
Yeah, intensity, then the phase doesn't. Yeah, that's true. I mean, it's inherently, it's because ultimately it's the intensity, right? But you can, you are right. You can also do some other things. That's true, right? So, but light intensity is something that people use quite a bit, right? You can certainly detect the phase or other things. Maybe more complicated, and then you may. So it's you could definitely try to explore other venues for the light, right? Yeah. Oh, yes, some question.
So you had a ring mechanism there, right? So for the matrix multiplication at first.
Uh-huh.
So how many of those operands X and W you can actually have them in one ring?
Oh, that's a great question, right?
Because
So-
the size increases.
Yeah, no. So because on one hand, we want to make the ring size smaller, right? Because we said, but there's some physics limits. So people in optical device, they always want to, it's like a Moore's law for like transistors, right? You want to, but because of some physics, so somehow, then with that, we find that you cannot chop it into too many, because then they will interfere with each other, right? So 4 or 8 probably is the most right now. Oh, we haven't, we only did, I forgot, when we tap out the, I think 4, I don't remember now, something like that. Not like 100, 200, right? Because then, yeah. But we want to essentially try to demonstrate the concept. That's, oh, wow, that's cool, you can do several things with one ring, right? So, yeah.
So if you want to do a bigger matrix multiplication, then you need to have them in sequence, all of those rings, or how the architecture scales up if the matrix multiplication or the matrix are bigger.
Oh, okay, great question. Right. So usually, right. So yeah, so if you have a huge matrix, right? So of course you probably cannot implement it in one optical chips, right? So you may have to do partition and so on and so forth. Right? So but the nice thing that you can reuse that because they are very fast. So then you have to have new architecture. Hey, because this is my basically tensor core. You can do whatever number of matrix multiplication, something like that, right? That's maybe 32 by 32 numbers, or pretty good. So then if you have a huge, even bigger ones, you just have to partition them and then reuse these and then somehow accumulate somewhere and stuff like that. Yeah.
I have one last question.
Oh yeah.
So when you're doing the matrix multiplication, so you have to put in only one single one single frequency.
No, that's a nice thing. Yeah, no, you can have different wave, it's called multiple wavelengths, WDM, right? Wavelength division multiplexing, right? You can have different wavelengths, and then, when they all come in, if you are talking about the intensity, you can kind of somehow, just get all of them, right? Then naturally, kind of can do, when you have multiplication and then you have accumulation, right? They can accumulate. Right? Yeah.
It's a current largest network, you've shown the transformers, right, on that simulation based.
Right, it's a simulation, right? That one
Largest network on a single chip right now.
That's a great question. So of course, if we are doing simulation stuff, but for fabrication, of course, universities don't have so much money.
Right.
They do have 2 companies, at least 2, probably more, right? Light Matter or Light Intelligence. I don't know whether they publish. I think 32 by 32, something like that. Or 64 by 64. I think 64 by 64. Yeah, 64 by 64. Because think about it, right? Area is no problem if you can kind of show this kind of order of magnitude improvement. There's a company called Cerebrus. I don't know whether you heard about it. Entire wafer is a chip. Or each chip is an entire wafer. It's crazy, right? So, NVIDIA, they're talking about the 80 billion or whatever number of transistors per chip. They're talking about 80 trillion. So it's like crazy, right? But of course, so, if there's a big need to build bigger tensor core, photonic tensor core, hey, I have a wafer, It's just what is ultimately what is worthwhile. So, and also if it is fast enough, right? So hey, you can reuse it, right? So the bottleneck is not necessarily the bigger ones. So anyway, there's a lot of interesting architectural things. How big is the biggest ones with the current area constraints, energy efficiency thing, right? So yeah, if you need, you can have a bigger one, I guess. Yeah.
One last question from me.
Sure.
So what's your take on the evolution of the size of electronic component? As right now the interest is growing in this area.
Yeah.
Do you see people working towards reducing the sizes of the component?
I'm sure people are doing that, but there are also other things, right? I mean, photonic, there are, I think, really other, not just the conventional. There is like a free space photonic. There are other. I think they're inventing maybe newer device, not necessarily trying to scale the new ring or micro disk. So I guess this is a very, again, very interesting kind of, so there's a lot of research opportunities to try even figure out the maybe other kind of, optical kind of device, plasmotic. I think there's one, yeah. So that can be even smaller, right? Much smaller, but yeah, the physics is slightly different, right? So this is a very interesting thing, to work very closely with those device people, to really see her. Because there's no one winner, like win all at this stage, right? It's not like a transistor people, or that's just continue scaling. That's it, right? So of course, when we scale now, the people also always come up with new architecture like FinFET, which is really a new device, and people are now doing 2D material or maybe 3D or get all around or then vertical. I mean, people are also talking about monolithic 3D kind of, PMOS on top of NMOS and stuff like that. But they're not quite. I mean, yeah. But for photonics, it's even more like so many different things. Yeah. I think on one hand, the classical device you try to scale, but then there's also new physics, new photonics. People are trying to look at that.
Thank you so much, Dave.
Okay, all right. Thank you very much.